You ever have one of those days where you just keep walking, wandering around aimlessly? Maybe you're circling a park, retracing your steps through your neighborhood, or looping around a hiking trail. Whether you realize it or not, two trusty concepts are tracking every move you make: distance and displacement. One is keeping a running tally of all your steps, while the other is eyeing your progress like a GPS on a mission. To break it down, we're going to dive deep into the world of scalars and vectors. By the end, you'll know exactly how far you've traveled and how far you've really gone. Distance, the path counter. Distance is your enthusiastic friend who loves keeping track of every step, every move, every twist and turn you take. If you walk from your house to the end of the street, then back, distance is thrilled. Look at you. That's 400 meters of walking. Doesn't matter that you ended up exactly where you started. Distance doesn't play favorites with direction. Distance is what we call a scalar quantity. It's pure magnitude, plain and simple. If your car's odometer reads 10,000 miles, that's distance for you. Just a big number showing how far you've gone, with no care in the world about where you ended up. Displacement, the shortcut enthusiast. Displacement is the focused friend. It cares about where you started and where you ended up, and it draws a straight line between the two. Displacement measures your net change in position, and it's a vector quantity, which means it comes with magnitude and direction. Not just how far, but in which direction. Let's go back to our street example. You walk 200 meters to the end of the street, then turn and walk 200 meters back home. Distance pats you on the back for walking a total of 400 meters. Displacement? It stares you dead in the eye and says, net change? 0 meters. You're right back where you started. It doesn't care how you got there, just where you are now. Real life analogy. Jogging around a track. Imagine you're jogging on a circular track with a circumference of 400 meters. You run one full lap. Distance is clapping, 400 meters covered. Nice job. But displacement? It's already moving on because you ended up exactly where you started. Net change in position? 0. To displacement, it's like you never moved. Draw a circle representing the track, with an arrow showing one lap and a label indicating distance as 400 meters and displacement as 0 meters. Why scalars and vectors matter? Why does this matter? Because in physics, direction matters. If you're trying to find out how far you've traveled overall, distance is all you need. But if you want to know how far you've moved relative to your starting point, or which way you've gone, you need displacement. Let's think about driving. Your car's odometer measures the distance you've driven, counting every mile no matter where you go. But if you need to know how far you are from home, that's a job for displacement. It tells you your straight line distance from point A to point B, with direction included. An example with a twist: walking the path. You're at the origin of a grid and you walk 4 meters north, then 3 meters east. Distance tells you you've walked a total of 7 meters. But displacement? It's already busy calculating. It draws a straight line between your starting and ending points and uses the Pythagorean theorem to find your net movement. Displacement calculation. Displacement equals the square root of 4 meters squared plus 3 meters squared. That equals the square root of 16 plus 9. That equals the square root of 25, which equals 5 meters. Displacement equals 5 meters northeast. In other words, displacement tells you exactly where you ended up relative to where you started. It's precise, directional, and to the point. Show a triangle with legs of 4 meters north and 3 meters east, and the hypotenuse labeled as the 5-meter displacement. Practical scenarios when distance and displacement collide. Running errands. You leave your house, drive 10 kilometers east to the grocery store, then turn around and drive 10 kilometers west home. Distance miles, noting you've driven a total of 20 kilometers. Displacement? 0, because you're back where you started. Crossing the ocean. A sailor travels 500 kilometers north and then 500 kilometers south. Total distance covered? 1,000 kilometers. But displacement? 0 again. Back to square one. It's like traveling in a big loop and ending up right where you started. Scalars versus vectors. Different worlds. To really get the difference, think about scalars as numbers that don't care about direction. Mass, temperature, speed, they just tell you how much, with no concern about which way you're headed. Vectors, on the other hand, are all about the numbers and the direction they're pointing. Velocity, displacement, force, these are all quantities with attitude. Imagine you're driving at 60 miles per hour. That's your speed, a scalar. But if you're driving 60 miles per hour north, now we're talking velocity, a vector. The direction makes all the difference. Vectors and direction, the magic of components. Now, let's dig a bit deeper. Vectors can be split into horizontal and vertical components, like breaking a push into two smaller pushes in different directions. If you push a heavy box diagonally, part of the force moves it forward and part presses it down. This makes analyzing motion easier, whether it's a ball flying through the air or a car driving up a hill. Want to see this in action? Imagine walking 5 steps east and then 5 steps north. Your net movement is along the diagonal, found using vector addition. Instead of simply adding 5 plus 5 equals 10 steps, vectors make you work for it. You need geometry to find the straight line path. Getting rigorous, a real challenge. Scenario: you walk 12 kilometers west, then turn and walk 9 kilometers south. What's your total distance traveled? And what's the magnitude of your displacement? Solution guide. Total distance: 12 kilometers plus 9 kilometers equals 21 kilometers. Displacement calculation using Pythagoras. Displacement equals the square root of 12 kilometers squared plus 9 kilometers squared. That equals the square root of 144 plus 81. That equals the square root of 225, which equals 15 kilometers southwest. Real-life applications. Pilots, sailors, and engineers. Pilots don't just care how far they fly. They need to know where they end up, considering wind and other factors. Using vector addition, they find their true path through the skies. Sailors use similar principles to navigate currents. Engineers designing bridges or roller coasters use displacement to ensure structures remain stable. Vectors also describe fields like gravity and magnetism, showing how forces act in space. Electric fields, magnetic fields, all governed by vectors. This helps predict how objects move and interact on a massive scale. Recap: the power of motion. To sum it all up, distance measures every inch of the journey, every step, every turn, no matter where you end up. Displacement focuses on your net change in position from start to finish. Scalars give you magnitude. Vectors give you magnitude plus direction. Together, they help us measure and predict motion, whether it's walking down the street or launching a spacecraft. So next time you move, ask yourself, how far did you go and where did you end up? Because sometimes it's not just about the journey, but where it takes you.